Okay, let's start part two of chapter 2, Turbomachinery. So we're going to go ahead and launch into an example problem here. The example problem reads, a centrifugal flow turbomachine has the relative velocity components as indicated in the figure below. Additionally, the following are specified. So we have given the the tangential velocity of the rotor at the point of entry of the fluid is 3.75 meters per second, and the tangential velocity of the rotor at the exit of the fluid is 7.5 meters per second. We have 57 kilograms per second worth of mass flow. The problem statement also gives us that the relative velocity of the entering fluid, again, that's the relative velocity between the absolute velocity of the entering fluid to that of the tangential velocity of the rotor, is 3 meters per second in the vertical direction. And then for relative velocity at the exit, it's 8.7 meters per second at an angle of 30.45 degrees to the horizontal. So the problem is asking us to determine the power and to classify the device as a turbine or a compressor, and also to find the reaction. So what we're going to do is I'm going to go ahead and split this problem into two velocity triangles. So what we're going to do is take the velocity triangle for the entering fluid and the exiting fluid. So if I do that, I have here on the next slide, again, the first step in trying to complete the velocity triangles. I have the relative velocity of the fluid entering. Again, it's in a vertical direction. And of course, the tangential velocity of the rotor is in the horizontal direction. So if I'm going to try to complete this triangle, I would get that they're obviously these two are at a right angle, and then those two would, if I go ahead and complete the vector math or the triangle math here, I can find out what the absolute velocity of the entering fluid is. So by looking at this, we know that U1 is given, right? And VR1 is given. So those two components are known. They're given in the problem statement: the tangential velocity of the fluid of the rotor and the relative velocity of the entering fluid to that of the rotor. Since those two things are known, I know that VR1 is in the radial direction. So again, knowing that, I know that those two produce a right triangle to each other. Therefore, since the relative velocity is perpendicular to the tangential velocity of the fluid, I know that the tangential velocity of the entering fluid has to equal the tangential velocity of the rotor, right? Again, these two velocity vectors are at a right angle to each other, so the absolute velocity of the fluid would go in this direction. In order for all this math to work out, that means that the tangential velocity of the fluid must be equal to the tangential velocity of the rotor. For the second velocity triangle here, I'm given that the relative velocity between the fluid and the rotor is going at an angle of 30.45 degrees to that of the tangential velocity of the rotor. So therefore, again, in this case, U2 and VR2 are known, right? So those are known, and I draw those out. I know that U2 is equal to 7.5 meters per second. If I go ahead and I do this math right, if I wanted to go ahead and take VR2 cosine of alpha, right, so that gives me that VR2, again, according to the problem statement, VR2 is 8.7 meters per second. And I take that cosine of the angle, the relative angle between the fluid velocity and the tangential velocity of the rotor, I get 30.5 degrees. I compute that, that actually also equals 7.5 meters per second. So that tells me that the absolute velocity is perpendicular to the tangential, the absolute velocity of the fluid is perpendicular to the tangential velocity of the rotor, right? Again, if I try to compute V2, the absolute velocity of the fluid, that would be basically the relative velocity times the cosine of this angle. And that makes it 7.5 meters per second. So therefore, since the absolute velocity of the fluid is vertical, or is perpendicular to the tangential velocity of the fluid, there is no tangent, sorry, the absolute velocity of the fluid is perpendicular to the tangential velocity of the rotor. That means the tangential velocity of the fluid is 0. So, just to reiterate with these velocity triangles, right? These velocity triangles must obey a fundamental equation. It must obey that the velocity of the fluid is equal to the tangential velocity of the rotor plus the relative velocity between the tangential velocity of the rotor and the absolute velocity of the fluid. And so in this problem statement, for the exiting fluid, since the exiting fluid absolute velocity is perpendicular to the tangential velocity of the rotor, that means the tangential component of the exiting fluid is 0. And for the entering fluid, it was stated that the relative velocity between the tangential velocity of the rotor and the absolute velocity of the fluid is perpendicular to the tangential velocity of the rotor. That means that the tangential velocity of the fluid is equal to the tangential velocity of the rotor. I know this could be a little confusing because there's a lot of, in explaining all of this, the word velocity is repeated several times, and hearing that could get you a little bit lost into the midst of things. So let's go ahead and rewind one more time and just recap what we're looking at to make sure that these things are clear. The problem statement gives us two things. Well, it gives us several things. It gives us what the tangential velocity of the rotor is at the entry point and the exit point of the fluid. So we have those numbers. It also gives us what the relative velocity between the fluid and so it's the relative velocity between the fluid's velocity and the tangential velocity of the rotor, right? It gives us that at the entry point and at the exit point. At the entry point, it's vertical. At the exit point, it's at an angle of about 30 degrees. So looking at those, at each point here, the rotor has a tangential velocity going in this direction. And here, the rotor has a tangential velocity going in the same direction as well. So if I go ahead for the entry direction here, right, I have my velocity triangle. Here's the relative velocity and the rotor. Adding those two together get me the absolute velocity of the fluid, right? Again, must obey this, this equation. So with that, if I go ahead, and since these two velocity components are perpendicular, since those two velocity components are perpendicular, go ahead and erase some of this. That means if I go ahead and try to find the tangential velocity component of the fluid, it's going to equal the tangential velocity of the of the rotor. Now, for the exit, it's similar logic, right? So for the exit fluid, for the fluid exiting, I get, again, the relative velocity and the tangential velocity. The math works out that if I try to compute what my absolute velocity of the fluid is, right, I take this angle and I take this value and multiply by the cosine of this angle, I get 7.5 meters per second in the vertical. Right, I get that in the vertical. So if that's the case, that means there is no tangential component, right? Because the entire direction is in a vertical direction. I hope that clears things up a little bit. Knowing these velocities now, we can go ahead and move forward with, for example, computing the power. So if I pull my equation from a prior slide, right, I can simplify this equation knowing that VU1 is equal to U1, so I get U1 multiplied by itself, minus U2, and I know that VU2 is 0. So this equation reduces down to m dot U1 squared, and I can fill in my numbers, making sure I get my correct conversion factors in there, right? So I have kilograms per second, meters squared per second squared, multiplied, so I get 1,000 meters squared per second squared is 1 kilojoule per kilogram. I get that my power is equal to 802 watts. Right, so that's the first component. It's asking what is the power. Second part was asking, is this turbo machine a turbine? Is it a turbine or a compressor? Again, it's pretty simple to figure that out. If you just take the product between the radius multiplied by the velocity of the tangential velocity of the fluid, you'll find that that moment is greater at the entrance than it is at the exit. So you end up with this being a turbine, right? I'm not given what the radius is, but I know that the tangential component at the exit is 0. So there's no choice but this component to be greater, right? So this ends up being a turbine. And then finally, we have here the reaction. All right, if we go ahead and plug in our numbers, I'm not going to do that, but if you just go ahead and take everything we just computed, you can figure out that this reaction is 0.87. Therefore, in this particular example, it's a reaction turbine. The static change, in this case, would be dominant. All right, so that's the first of 2 example problems that we're going to go ahead and do for this chapter. But this example, the end of this example problem will signifies the end of this video. Thank you.